Okay. It is my great pleasure to introduce Leslie Lamport from Microsoft Research. Leslie is best known for his seminal work in distributed systems and as the initial developer of the document preparation system, LaTeX, which a lot of us use every day. Leslie won the 2013 Turing Award for imposing clear, well-defined coherence on seemingly chaotic behavior of distributed computing systems in which several autonomous computers communicate with each other by passing messages. He devised important algorithms and developed formal modeling and verification protocols that improve the quality of real distributed systems. These contributions have resulted in improved correctness, performance, and reliability of computer systems. So please join me in welcoming Leslie Lamport.
Thank you. There are some still seats over there. I do not bite or throw things. It's safe. I want you to listen carefully because there's going to be a quiz at the end of the talk. But it's not a usual kind of quiz. Instead of answering questions, you're going to have to ask questions. And so at the end of the talk, I'm just going to choose random people and ask you to ask a question. So you should be prepared. Okay. If you're not writing a program, don't use a programming language. Tony Hoare, someone who won the Turing Award a couple of decades before I did, wrote that inside every large program, there's a small program trying to get out. What he meant, and I think what we would say these days, is that there's an algorithm trying to get out. So what's an algorithm? I'll give you an example of a simple algorithm that I think many of you probably have seen. It's Euclid's algorithm for computing the GCD, greatest common divisor, of two integers, of two positive integers. Let's call them m and n. And GCD of m and n is the largest integer such that both n and n are multiples of that integer. And here's the algorithm. Let x equal m and y equals n, and repeatedly subtract the smaller of x and y from the larger, and stop when x and y have the same value. And that value is the greatest common divisor of m and n. A very beautiful, very simple algorithm. Euclid's program. Well, he didn't write programs, but what if you were writing a program to implement Euclid's algorithm? Well, you'd have to add a lot of lower-level details. What are the types of m and n? Int, long, some big integer class. What do you do if m or n is less than or equal to 0? The program has to do something if you get a bad input. Should it throw an exception? Should it simply assume that it can't happen and the user beware? There are a whole bunch of questions of lower-level details that have to be answered to write a program. But they don't appear in Euclid's algorithm. So algorithms versus programs. Well, there's no precise difference. But algorithms are more abstract, that are higher level than programs. I mean, programs are written in a programming language, but algorithms don't have to be. And inside every large program, there is an algorithm trying to get out. Usually, it's not the kind of algorithm that you learn about in an algorithm class, or that most people call an algorithm. It's usually useful only in that particular program. And it tends to often be more complex than the kinds of algorithms that, like Euclid's algorithm, that you learn about in an algorithms class. Sometimes they're called a high-level design or a specification or a model. But I'm going to call them an algorithm. And that's trying to get out. I'm not sure if they're trying or not, but They should get out, is what Tony meant. And they usually fail to get out because the programmer doesn't know it's there. Because you can't see it if you're thinking in terms of code. And the result? Imagine trying to write a program to compute the GCD by thinking about coding details like types and exceptions and classes and all of that stuff, instead of thinking about the mathematical properties of numbers. The program would be hard to debug because you'd be debugging an algorithm at the code level. And all the techniques of debugging you've learned are about debugging code. You're very good at debugging code, but they're terrible at debugging an algorithm. And the program would be inefficient. And because you'd be trying to optimize an algorithm at the code level. And the result is that programs are hard to debug and inefficient these days. So what should we do? Well, we should do what almost every other field of science and engineering does. Describe algorithms with math. And how do we do it? Well, lots of methods have been proposed, and some of them are even useful. But there is one that's most generally useful in practice for both sequential and concurrent or distributed algorithms. And here's how it works. You describe an execution of the algorithm as a sequence of states, where a state is an assignment of values to variables. So for example, here's Euclid's algorithm described as a sequence where execution is described as a sequence of states. Start, say, for m equals 12 and n equals 18. It starts in a state in which x has the value 12 and y has the value 18. Then in the next state, well, you subtract the smaller of the two from the larger, so you subtract x from y, and you wind up with a state where x is 12 and y equals 16. And then subtract the smaller from the larger, you subtract y from x, and you wind up with a state in which x and y both equal 6. And then you stop because your algorithm stops when x equals y. Now, I'm going to call sequences of states behaviors, just a very simple word for it. And I'll call pair of consecutive states a step. So here's one step, and here are two steps in this behavior of Euclid's algorithm. So an algorithm is described by describing its executions as sequences of states. So how do we describe those sequences of states? Well, we describe them, again, by a set of behaviors. The set of all behaviors representing possible executions or legal executions of the algorithm. And for any m and n, Euclid's algorithm has one possible execution. So it's described by a set consisting of a single behavior. But concurrent and distributed algorithms tend to have lots and lots of possible executions. So they're described by large sets of behaviors, often infinite sets. But math has no trouble describing infinite sets, so don't worry about that. So how do we describe this set of behaviors? It's a very simple way to do it. We describe it by an initial predicate on a state. A predicate is just the mathematical term, means a Boolean valued function. So we have a Boolean valued function on states. And second thing, a next state predicate on pairs of states. Some function, a Boolean valued function on pairs of states. So a behavior, which is a sequence of states, S1, S2, S3, etc., is in this set described by these two predicates, if and only if the initial predicate is true in the first state, and the next state predicate is true on each step, each successive pairs of states and the behavior. This state, step, and so on. So let's look at that for how that works for Euclid's algorithm. The first an initial predicate on states. Can you guess what that is? It says x equals m and y equals n. Now this funny symbol, I don't know if you've seen it in your math classes, that means and. Mathematicians are still living in the 17th century and they're writing formulas with words. So mathematicians might say x equals m and y equals n. But we're going to enter the 20th century at least, and we're going to write formulas in math, not using words. The next state predicate on pairs of states. Well, there's two parts. Here's the first part, and here's the second part. So that symbol means or. So this formula is true if and only if either this part, which is this and this and this, or this part, this and this and this, is true. And remember, it's a predicate on pairs of states. And in this formula, the unprimed variables are going to refer to the values of those variables in the first state. And the primed variables are going to refer to the values of the variable in the second state. Okay? So what does this say? First it says x is greater than y, and x prime equals x minus y, and y prime equals y. Well, x is greater than y. That means when x is greater than y, this applies. This says the new value of x equals the value of x in the second state equals its value in the first state minus the value of y in the first state. In other words, that's what subtract a y from x means. And this part says that the new value of y, the value of y in the second state, is equal to its value in the first state. So it means leave y unchanged. So that's that formula. Of course, the second part of the or, first part handles the case when x is greater than y, and the second part describes the analogous thing when y is greater than x. So that's the next state relation, next state predicate for Euclid's algorithm. I'm giving these names, next e and init e, just giving names to those formulas. And notice that this formula is false if x equals y, because neither of those two ors is true, because the first part equals false, the second one equals false, and false or false equals false. So false means no next state satisfies that formula, and therefore there's no next state in the behavior, and the algorithm holds. So we've represented Euclid's algorithm by two formulas. One I've called init e and one I've called next e. We don't need any programming languages to describe Euclid's algorithm. Look how nice and simple it is, just described by this mathematical, these two simple math formulas. It's all just simple math. I mean, just a little arithmetic, greater than minus, and then just these two, and or. And you just need simple math to describe algorithms, unless they're algorithms that happen to perform some kind of complicated mathematical calculation, in which case you're going to need some math. I mean, if one step of the algorithm says find the solution to this differential equation, well, that's going to be a little complicated to say in math. That might take you 10 lines or so. But most of the algorithms you deal with described by this simple math. So what could be more beautiful than describing Euclid's algorithm by two formulas? Anyone want to take a guess? One formula. Ah, great. You guys have a sense of mathematical aesthetics. Perfect. So a behavior represents an execution of Euclid's algorithm if and only if init is true on the first state and next is true in each step. And I'm going to write this as a predicate on behaviors. That is a formula that's true or false on behaviors as follows. This part, init is true on S1, I'll just write as init. Because we're going to interpret a state predicate as a predicate on behaviors if it's true on the first state of the behavior. And next is true on each step. We'll write that part this way, where box is this funny mapping from predicates on pairs of states to predicates on behaviors. Giving a predicate on a pair of states, you write a box, and it means that that's true on each step in the behavior. Okay. Funny symbol. It's read always. So here's this one piece of math that you haven't seen. Okay? That's the only piece of math that you haven't seen that you're going to see in this talk. Okay, predicate on behaviors, and instead of calling it a predicate on behaviors, I'll call it a property. So a property is a predicate on behaviors. So this is Euclid's algorithm written in math. And these are, remember, these are just abbreviations. You know, init E is defined to equal that formula. In other words, init E is just an abbreviation for that formula. And that's what a definition means. It says definition is just an abbreviation, a shorter way of writing something. So this formula on top is just an abbreviation for this one. Simple enough that you don't really need an abbreviation, but it's nice to use abbreviations. Okay? Isn't this beautiful? If you think it's beautiful, raise your hand if you think this is beautiful. Well, a few of you. Okay. It takes a while to, appreciate beauty. Did you appreciate how beautiful Picasso is the first time you saw one? It takes you getting used to things to think they're beautiful. But in science and engineering, beauty isn't the goal. But it is a sign that we're doing something right. Okay, so here we are. Now, for m equals 12 and n equals 18, that formula is true on this behavior. Well, it's also true on this behavior. Those two conditions are satisfied. And this is also true on this condition. In other words, the next predicate is true on every step because there are no steps. And therefore, for every step, that formula is true. So we want to rule out these behaviors. And the usual way, the obvious way, the way any computer scientist, almost any computer scientist but me, will tell you how to do it is simply don't allow it to end in a state in which the next step is impossible. Or rather, on which if you can take a next step, do it. That's the obvious way, but it's not a good way for reasons that I'm not going to really convince you of. But basically, we need something more general. And sometimes it's not always desired. Sometimes you want to allow programs to stop, algorithms to stop. For example, if an algorithm responds to behaviors, to inputs, you don't want to require that it always get inputs. So you want to allow it to stop if there's no input. So safety and liveness. There are two kinds of properties that you should know about. A safety property asserts what's allowed to happen. For example, the algorithm is allowed to output a value if it's the correct value. A liveness property asserts what must eventually happen. For example, the algorithm must eventually produce an output. The Euclid's algorithm And for any algorithm, those first two parts, init and box next, is a safety property. It says what's allowed to happen. It describes what steps you're allowed to take, but it doesn't say you have to take any steps. What we need to add to it is a liveness property that says if it can take a step, it should take a step in order to rule out premature stopping. Now, programming languages, they usually don't tell you anything about liveness. They usually just sort of make the tacit assumption that, the program will keep taking next steps. They might have some other primitive notions of liveness if they're a concurrent programming language. But if you really want to describe more interesting liveness properties, like under certain conditions it's allowed to produce an output, you have to write complicated code to describe it. Now, I'd love to show you how easily math can express liveness. And in fact, that box formula, that always formula, is the key to how you do it. But I don't have the time. So I'm not going to talk about liveness. But what you should know is that any property can be written as the conjunction, as the and of a safety and a liveness property. Safety and liveness can be described mathematically. If there were a mathematician here in the audience, I could explain in terms of topology what it means. But I could also explain it, take 5 minutes and explain it in ordinary language. But I'm not going to do it. I'll only discuss safety. Invariance. Partial correctness of Euclid's algorithm. I don't know if anybody heard the term partial correctness? Yeah, some of you have. That says that if it has terminated, then x is equal to the GCD of m and n. And that's the property that you want Euclid's algorithm to satisfy. So you know when it stops, x equals y, so both x and y will equal n. But this is the property that we want, the safety property that we want Euclid's algorithm to satisfy. And remember, that terminated means x equals y. So if then, I'm sorry, I guess there's another symbol you have to see, implies, that's how mathematicians write, means this implies something, which means if this is true, then the next thing is true, and that's logical implication. Also written in these ways, I don't know, you may have seen it with some other notation. But that's the formula that is expressed by if the algorithm is terminated, then x equals the GCD. Now, partial correctness means that this is true for all states of the behavior. Of course, we know it's only possible that it'll happen, if it happens, it's going to be the last state. But correctness means that for any state it reaches, if x equals y, then x equals the GCD of m and n. That's the safety property. And we stay true for all states of the behavior by putting a box in front of it. Because, after all, this formula is the same kind of formula as the next state. It's the next state formula, but it just doesn't have any primes in it. So, of course, what this means is that that formula is true in every state. Or, if you like, it's true of the first state of every pair. And partial correctness means if a behavior is allowed by the algorithm, then it satisfies this property. But a behavior allowed by the algorithm is expressed by this formula. If then it satisfies this property, we write this way. So satisfying a property is just logical implication. Isn't that elegant? So such a property is called an invariance property. And that the property with satisfying a property means the formula that describes the algorithm implies that property. A property that begins box and a formula about state, predicate on states, is called an invariance property. And that property on states is called an invariant. That's just a bunch of terminology, just giving things names. So proving invariance, I'm going to skip through this. How many of you want to see how to write, how to prove this? And how many would rather I go on to, not spend the 10 minutes on that? You raise your hand. How many of you would like me to just stop talking? Well, I can't tell. I feel like skipping it. But I'm going to just show you what it is. We prove this formula, where say that IE is an invariant, by proving these two mathematical formulas. So the prop, and it'd take me about 5 minutes to convince you that, in fact, these formulas are the ones you have to prove. And this IE prime, priming a formula means you prime all the variables in it. So IE prime means that IE is true in the second state, and IE means it's true in the first state. So this first proposition is about states, and the second proposition is about steps. But really simple. And something satisfies these two steps. It's called an inductive invariant. Now, x equals y implies x equals GCD of ebb and n. That is, partial correctness is not inductive. The reason is it's easy to see that it's not going to satisfy this, because this means it gets satisfied by every possible state. And a state is just an assignment of values to variables. So basically, start in any state in which, say, x is greater than y and x minus y equals 0, even though the GCD of x and y can be anything. And that formula is going to be true because x equals y will be false in the first state. And therefore, this formula is going to be vacuously true. So the left-hand side of this, so I sub e is going to be true in the first state. But once you subtract x from y, you're going to say true implies this, which is equivalent to this, and x does not necessarily have to be the GCD. So the way we prove an invariant that's not inductive is by finding an inductive invariant that implies it. And the inductive invariant for Euclid's algorithm is this, that the GCD of x and y is always equal to the GCD of m and n. That means in every state of every execution of Euclid's algorithm, that formula is true. Now, what an algorithm does next depends on its current state, not what it did in the past. So an algorithm satisfies a safety property because it maintains some inductive invariant. And so Euclid's algorithm computes the GCD, or that is, if it stops with x and y equal to the GCD because it maintains this inductive invariant. How many of you knew that? A couple. How many of you have studied have seen Euclid's algorithm? So most of you have seen Euclid's algorithm without really understanding why it works. And it works because it maintains this inductive invariant. To understand an algorithm, you need to know what its inductive invariant is that makes it work. So that's how we prove it. And there are various methods for proving correctness or proving safety properties of algorithms. And they all boil down to this little bit of mathematics, but they usually they hide it often by writing the inductive invariant as an annotation of the program, or find some other ways of hiding the mathematics, because they don't want to frighten people by mathematics. Don't be frightened by mathematics. Mathematics makes things simpler. This is simpler, easy to understand, a lot easier to understand than all the ways that people have of telling you how to reason about programs that try to avoid talking about mathematics. Things get simpler when expressed in math, especially instead of if you get much more complicated if you try to express them in terms of a programming language. Okay, let's take a little closer look at formulas. In mathematics, writing a formula with variables x and y doesn't mean that there are no other variables in the universe. It just means that this formula is just saying nothing about any of those other variables. I mean, a state is an assignment of variables. Well, what variables? All possible variables. X, Y, Z, bar, population of Iran, so on. This describes Euclid's algorithm. No, it's not describing Euclid's algorithm. It's describing a universe in which the values of x and y represent an execution of Euclid's algorithm. It just doesn't tell you about, all the rest of those infinite number of other variables. The problem is that this formula asserts that every step changes x or y. So it describes a universe in which the value of the population of Iran can change only when the value of x or y in Euclid's algorithm changes. So when you write Euclid's algorithm, you're saying, nobody can get born in Iran until this algorithm takes a step. Obviously, that's pretty silly. What the way of eliminating that silliness is by saying that a formula, a property like this, should allow steps that leave x and y unchanged. In other words, this should actually be what the next state relation is. And I have an abbreviation for it. Just write it this way. No, doesn't mean anything particularly interesting. Just that's an abbreviation for saying each step is either satisfies next E or it leaves both x and y unchanged. So this is the formula that describes a universe containing Euclid's algorithm. It requires some very obvious changes to the formulas I just wrote, but it adds a few more characters, but the formula is basically the same. And so remember, though, this is the safety part. And this allows behaviors. Not only does it allow behaviors of Euclid's algorithm with steps in between, but this allows behaviors in which x and y never change. But that's where the Leibniz property comes in. That must rule out such behaviors. And it's no big deal. Implementation, also known as refinement. Suppose we have some algorithm, machine Euclid, that implements Euclid's algorithm as it might be executed on a computer. So for example, it represents integers as arrays of 32-bit words. So the operation of comparing and subtracting integers might be represented by multiple steps. In other words, if you look at the circuitry that goes on inside of doing subtraction of 32-bit words, well, maybe it'll take 80 steps to do a single subtraction. Now, ignoring liveness, we can represent machine Euclid by the same kind of formula. Initial predicate, box, the next state relation, and a list of its variables, which allows steps that don't change any of those variables. So algorithm machine Euclid implements Euclid's algorithm. What does that mean? Well, I'll show you. It means that this formula is true. So, see what this formula says. This is just machine Euclid. This implies, that means that every behavior of machine Euclid satisfies the thing to the right of the implication. This is Euclid's algorithm. And this is a substitution. These are expressions containing the variables of machine Euclid. And what those formulas do is tell you how those 32-bit values, or stuff that's stored inside this machine Euclid program, which works with arrays of bits, how they represent the value of x and how they represent the value of y. And this just means substitution. So this says that is this formula Euclid with these expressions substituted for x and y. Now, mathematicians have no standard notation for substitution, so that's why I had to write it this way. And remember, this is just an abbreviation for this formula. So this literally means you take this formula, and then every place you see an x, you replace it with this stuff, and every place you see a y, you replace it with this stuff. So Euclid's algorithm, with each occurrence of x and y replaced by the expression of machine Euclid that implements it. And that's what implementation means. Now, you don't have time to show you why this is the right definition. It's not obvious, and most people don't see it right away. But take my word for it. When I analyze exactly what each formula does and what it means and what this means in terms of behaviors, you'll say, oh, yes, that's the formula. But you should see how simple and elegant it is. And to prove it, we find some suitable invariant of the suitable inductive invariant of machine Euclid. And we prove these two formulas. And again, don't bother looking too hard at them, but just look at how simple they are. Just two formulas. Just ordinary math. And it explains why, the variant explains why machine Euclid implements Euclid's algorithm. And you're not going to have to explain why it computes the GCD, because it implements Euclid's algorithm, and Euclid's algorithm implements the GCD. That means that the GCD of these two formulas that represent x and y are going to wind up being the GCD of M and N. Now, implementation involves substituting expressions for variables. That's an ordinary mathematical operation. People do it in your math classes all the time. It's what people really mean if they talk about data refinement. But you can't do such substitution in a program. So you can't even talk about what implementation means in terms of programs, in terms of programming languages. You can't substitute some expression for a variable in a programming language. What does it mean to say that, if you say x gets x plus 1, well, what does it mean to substitute a plus b for x in that assignment? I don't know. Just myself. How do you even define how do you define what it means for one program to implement another? You have to translate the programs to mathematical formulas and use this definition. Now, translating a program to mathematics is what's called giving semantics to a program. So if this is machine Euclid is a program, and this formula is this mathematical translation, then that's what it means for the program to implement Euclid's algorithm. Now, programming languages are very complicated. So the mathematical translation of the program is going to be very complicated. You're generally not going to be able to actually write down that mathematical formula and actually write a proof that your program implements Euclid's algorithm. But that's okay, because you should understand, when you understand the concept, it tells you what you need to do to implement Euclid's algorithm. So you have this intuitive understanding of exactly what it means for the program to implement Euclid's algorithm. And that helps you get the program right. Even if you don't have the time and effort to actually prove that it does. But it does mean that you certainly shouldn't use programming languages to write algorithms, because then you have to worry about the right-hand side of that implication. Now, everybody will tell you, any programmer, if they're practicing programmers here, you're going to say to yourself, oh yeah, that looks really great. Math works on tiny examples. But everyone knows that it doesn't work in the real world. You just can't do that with real algorithms. They think you can't. The only difference between Euclid's algorithm and the algorithms inside of real programs, real systems, is the size of the formulas. So instead of 6 lines, you may have hundreds of lines. Now, large formulas, the way you handle large formulas, large programs, large anything, is by hierarchical decomposition. Mathematics has the simplest and most powerful method of hierarchical decomposition known to man, the definition. So if I want to hierarchically decompose this, you give names to subformulas. I might call that subformula decrement X, decrement Y, and then I'll define next to be decrement X or decrement Y. And then there's the definitions of decrement X and decrement Y. Nothing difficult, nothing, no classes and procedure calls and all that horrible, complicated programming language stuff. Just definition. And that allows you to express, much more expressive than what programming languages provide for hierarchical composition. And the reason is that I can write a definition to any little part of the subformula that I want. And that gives me much more ability to do useful hierarchical decomposition to make a formula easy to understand than you can do with a program using a programming language. Okay, describing algorithms of math in the real world and beyond. Rosetta, that was a spacecraft that European Space Agency sent to explore a comet. And several of its instruments were controlled by a real-time operating system named Virtuoso. And people who built Virtuoso decided to build the next version of it. And they decided to write a precise mathematical definition, a mathematical algorithm that describes its higher level design, or at least some aspects of its higher level design. They described it in TLA+. TLA+ is a language that I developed. Basically, it's just a formal language for doing mathematics and for writing exactly the kinds of of algorithms that I showed you with Euclid's algorithms, just that mathematicians don't, or very few mathematicians, or hardly any mathematicians, actually write rigorous formal mathematics. And you need to write it in a precise language if you're going to make tools. And so I had to, invent a precise formal language, and it looks very much like ordinary math, except it has some notations for things that mathematicians never felt the need to write notation for, and so, it won't look completely familiar to you, but you can very quickly learn those few notations, and it becomes ordinary math. Now, the head of that team that wrote this second version, wrote Virtuoso in the second version, and Eric Verhulst. And I asked him how it went, because I did do nothing. I didn't know that they were doing it. Somebody told me about the book. Here's what he told me in an email. He said the TLA plus abstraction helped a lot in coming to a much cleaner architecture. He also said, we witnessed firsthand the brainwashing done by years of C programming. Now, not all programming languages are as bad at C at that, but they're all brainwashing to some extent, because they get you thinking in programming terms instead of in mathematical terms. And one of the results was that the code size is 10 times less than it was in the original system. You may have all heard about the second system effect. People build a second system and they want it, do everything the first system did and everything, as well as adding some new stuff, and it becomes much bigger. This one became 10 times smaller. And you don't produce 10 times less code by better coding. You produce it with what he called a cleaner architecture, and what I would call a better algorithm. With that better algorithm comes from mathematical thinking. This really works. You don't get that from thinking in the programming language. Okay, from space to the clouds, descending. Paper was published by Amazon Web Services, uses formal methods, published about 5 years ago. Amazon Web Services are the people that build Amazon's cloud infrastructure. And it's about, they talk about formal methods, but the formal method they use is this TLA plus language and its tools. And here are the key insights that they said. Formal methods, and by that they mean TLA plus mathematical methods, find bugs in system designs that cannot be found through any other technique we know of. And the reason for that, they know lots of techniques for finding bugs in code, but those techniques don't work for finding bugs in algorithms. Formal methods are surprisingly feasible for mainstream software development and give good return on investment. These are not some pie-in-the-sky, theoreticians. Amazon doesn't, care about how elegant or how beautiful something is. They say, is it going to save them money? Or are they going to be able to produce the software with the reliability that they need more cheaply than any other method for doing it? And at Amazon, formal methods are routinely applied to the design of complex real-world software, including public cloud services. You can read it and look it up in Communications of the ACM. TLA Plus is also used at Microsoft, and its bigger user is the group that builds Azure, which is Microsoft's cloud services infrastructure. And there's a real reason for that, because that it has gotten popularity in cloud services. And not only Intel has been, some people at Intel started using it 20 years ago, but they really care about getting things right. And they know how hard it is because they have programs, I mean, their systems, they have millions of users that are banging on their system 24 hours a day. And if there's a bug in their system, it's not a question of if it will appear, it's a question of when it's going to appear, because it's surely going to appear at some point. Now, TLA Plus has industrial strength tools for checking invariance and liveness properties and implementation. That's not the best language to describe all algorithms. Not all algorithms are worth describing in a completely formal language. And the TLA Plus tools aren't useful in all application domains. But TLA Plus shows that describing algorithms with math works in practice, and that thinking mathematically helps you build better systems. Inside every large program, there is an algorithm trying to get out. Every large program. And you should find and understand that algorithm before you start writing the program. And the best way to understand an algorithm is to describe it with mathematics. And if the algorithms inside the complex distributed systems of Amazon and Microsoft can be described with math, then your algorithms can be as well. So don't be brainwashed by programming languages. Free your mind with mathematics. Thank you.
So we have a fair bit of time for questions. So can we have somebody?
Yeah, call on, choose a random person.
Oh, choose a random person. Roland always has a question.
Random, right?
Random, very random, very random.
Okay, so let me ask a basic question. So I agree with much of what you said. I didn't quite understand, at least for sequential code, the difference with Hoare logic.
The difference what?
The difference with Hoare logic.
The difference in quality.
No, with Hoare logic. The standard verification approach for sequential programs is Hoare logic.
Oh, Hoare logic. Well, I said Hoare logic is actually equivalent to Floyd logic.
Or Floyd logic, yes, of course.
And what that does is it writes the invariant as an annotation to the program. It says the inductive invariant is written in principle at each control point in the program. You write what is true when control is at that control point. And it's a fine method. I mean, and in fact, I have I developed a language that's called PlusCal, which looks like sort of an ordinary toy programming language, but it gets translated to TLA Plus, and then you could apply the TLA Plus tools for it. And a lot of people, especially for sequential algorithms, find that more useful than doing it directly in TLA Plus. I said it looks like a toy programming language, but the one thing that distinguishes it is that the expressions in that language can be literally any mathematical expression. So I can write a statement that says, if Fermat's last theorem is true, then do this, else do something else. And that would be one program, that Fermat's last theorem is true. It's simply a mathematical formula. And the tools can execute that, but on models. So it will basically say, instead of, there is no natural number for satisfying this property, well, you have to substitute natural numbers, from 1 to 100, and it'll say, well, Fermat's theorem is true for numbers from 1 to 100. But at any rate, that's a fine method. It turns out for concurrent algorithms, in fact, one of my first paper in the field of that was an extension of Floyd's method to concurrent algorithms. And I eventually came to the realization that it's better not to write the inductive invariant as an annotation, but to just write a single annotation, and to not write the algorithms in terms of something that looks like a programming language, but to do it in mathematics. So, as I said, those two rules that I gave you for proving that something is an inductive invariant, that's exactly what the Floyd-Hort method is doing, but they hide the mathematics to some extent.
Okay, so is it, maybe just to paraphrase, I think what you're saying is that the development style is different, but maybe the technical math is essentially the same. The technologies we use to prove those things are essentially.
Yeah, but remember, that's just talking about proving invariance. The Floyd methods tells you nothing about how to prove that one algorithm implements another, or that a program implements an algorithm. For that, you need to really be at the mathematics level. And you should, if you want to use the Floyd method and you like it, it's a fine method, but you should understand the mathematics underneath it. You should understand what it's doing, that your algorithm program is an initial predicate and a next state relation, and what the method is doing is splitting the proof of those two conditions for proving invariance into separate pieces.
Thank you very much. It's a beautiful talk, and I very much agree with the message. I'm curious about the experience at Amazon and perhaps Microsoft of connecting the formal result obtained for the model of an algorithm of a system to the actual implementation. So how the developers convince themselves that what they have actually implemented corresponds to the beautiful algorithmic model that they have verified in TLA+.
They don't seem to consider that to be a problem. Or more precisely, I mean, they understand that there is something to be done, but they don't expect TLA Plus to solve that for them. And I would like, to find more, direct connections. For example, one thing you could do is instrument the code in such a way that it outputs the behavior that the programmer thinks is the behavior of your specification. And then you could apply our model checker to actually check if that behavior satisfies the specification. But the people in at Amazon or Microsoft just didn't, actually I didn't talk much at Microsoft, but the people at Intel, they didn't seem to be interested in that. But one thing I should mention is that they really trust TLA Plus at the algorithm level. And both the people at Intel and the people at Amazon have told me that they will make optimizations to their system, their design, and put them into the production code that they would not have otherwise done, except that having written them in TLA Plus and applied our tools to check them, that has given them the confidence to do that. So, people will say, oh, if you use these formal methods, you get less efficient code. And, Amazon and Intel will tell them, no, it's the opposite way around.
Hi. You mentioned that these these formal methods and maybe TLA Plus aren't necessarily the right tools for all kinds of problems and algorithms. So I'm wondering, what is the nature of that class of algorithms for which this doesn't really help?
I'm saying that TLA plus is not the answer to all these things, but I do say that mathematical thinking is the answer. If I look at, I haven't done very much programming since I made my living as a programmer 40 or 50 years ago, but I do some up to a few years ago. I used to do occasional programming and write some code for the TLA plus tools, and I used TLA plus or PlusCal. Over 15 years, maybe I've used it, 4 half dozen times. But every piece of code that I write, first of all, has a specification of what the code is supposed to do. Often, that's just a few lines of English. Sometimes it's more mathematical. It depends on how difficult that particular piece of code is to write. And occasionally, I think that that's hard enough to get right that I will write an actual TLA plus specification of it. And it's an engineering decision of how hard is this, how much, how important is the code, how much effort is it worth putting into getting it right. And there's no simple rule. One thing is often I might have done something, tested out in TLA plus, but for the particular tool, for what's going on is that I'm dealing with a piece of code that's sitting in the middle of a whole bunch of other code. And coding, remember, when you write a specification, you're specifying not just this code, you're specifying the whole universe, and in particular the environment. And the specification of the environment would have been too much work. Another way of looking at it is I would have to be able to generate tests that would have to duplicate what a whole bunch of other code is doing, and it was just not worth the effort to do all of that. But so, it just should be common sense. How important, how critical is this code, and how difficult is it?
Yeah, just to seed that a little bit, I was thinking something like maybe algorithms that aren't designed to stop, or say algorithms that are used in AI where the ultimate behavior isn't well defined, but how you process data would be, or something like that, where there's a class of algorithms that it would be difficult to use TLA for. But
well, I can almost categorically say that if it involves significant concurrency, then you should use something like this. Now, AI is a whole different ballgame because the whole idea of what I'm telling you about is that you should understand how your algorithms work. And the whole successful principle of modern AI is that we don't understand how to do this, but we can then train this program to produce a program that we don't understand, and therefore it does it. Now, this is a very serious problem. Now, we know that you can train these devices to have 99% accuracy. Well, someday this program is going to be driving my car, and I don't want to drive a car that has only 99% probability of thinking that that child crossing the street is actually a child and not a stone sitting there or something. So we need to figure out how to embed these programs that we don't know how they work, or the algorithms that we don't understand, inside of systems that we do understand well enough that we can trust them. I don't have a solution to this problem, but waving your hand and saying, oh, we'll invent a programming language to solve it is you know, it's not going to do it. This is a very serious research problem. And in order to solve it, one of the things you'll need to do is learn to think about algorithms mathematically.
Like two queries which I have. One is quite related to the presentation. Maybe I'm not well versed in that subject. So, like, can there be more than one inductive variant for the same case?
Oh, well, you could have two inductive invariants, but the conjunction of two inductive invariants is also an inductive invariant.
No,
so
it might be an OR process, like both are true, but they are separately true. So instead of a
well, you can, if they're independent, you can separate the proof into doing these two different pieces. I mean, there are, algorithms may do more than one thing, and you may have more than one invariance property that you want to prove about it. But whether you call it, say that you have, you know, two separate invariants or one invariant that's the conjunction of the two, they're mathematically equivalent. So, I mean, they may be mathematically equivalent if they're separately in each an inductive invariant. So it's just, what do you want to call it?
okay, and the second query which I had was like, are there cases of false positives in the, like you use how TLA plus would like gives a mathematical thinking to an algorithm and to a program. So any false positives could be like harmful. So have you come across any such?
Well, I don't know what a false positive means. You mean detecting an error that's not there?
Yeah.
Well, first of all, an algorithm has a mathematical formula. In other words, it's a definition. You know, an id, an init, and an xt are definitions. Definitions are not right or wrong. They're definitions. Now, when we say that an algorithm is wrong, what we mean is that it doesn't satisfy the properties that we think it should. And so the major tool used is a model checker. And the model checker basically works by taking a small model or a small instance of the algorithm and checking all possible behaviors. Now, you may get false negatives, and you know, you may miss errors because you haven't picked a big enough model, or but engineer, I mean, it's sort of engineering understanding, or is what tells you how big a model you need to take. An interesting anecdote which may be relevant is at one point the people designing a part of a chip for a DEC processor decided they'll want to try TLA plus. They assigned now hardware engineers, unlike software engineers, they write specifications. But before TLA plus, all they could do was write them in English with some pseudocode or something. So they wrote that kind of specification, and then they gave it to a junior engineer to write the TLA plus spec. And he didn't want to bother those senior engineers. So in writing the spec, specs are general, English specs are going to be ambiguous. And so he had to make his own decisions on what these meant. And in the course of the spec, he found 41 bugs. It turned out that all of them were bugs in his spec, that he went back and showed them to the engineer and said, oh, it wasn't supposed to do this in this case, it was supposed to do something else. But, so you say, oh, the TLA plus spec didn't help, any. But in those examples, they showed the engineers that their algorithm could reach states that they never thought were possible. And by examining that, and I forget whether they did it by putting tests of the RTL code or whether they're actually in the algorithm, but they actually found 4 bugs in the chip because of that, because it explained their algorithm that ways, things that they hadn't understand, weren't able to understand. So, it did help them understand, it was useful to them, in addition to giving them more confidence.
Hi, I have 2 questions. Firstly, you mentioned how TLA Plus was applied to verify hardware. Does TLA Plus natively support the synthesis and verification of hardware?
Nope, as I said, same as software. You cannot generate software automatically from a TLA Plus. You can't generate hardware automatically from TLA Plus. Wonderful if you can, but the more you try to do it, the easier you try to make it to go from the algorithm to the code, the worse your language gets for specifying the algorithms. Now, I think there are cases, there are special application domains, and particularly ones where you're not interested, you don't care that much about efficiency, where you could actually generate the code automatically. And I suggested that as a nice research topic, but nobody has done it. And as I said, the people in industry, I think they realize the the distance between algorithm and code. And they know that that's a huge gap, and they understand that trying to bridge that gap by bringing the algorithm down to a lower level is not the right way of doing it. On the other hand, at some point in Intel, I was told that the people who do the next state, the RTL, Register Transfer Language, description of the hardware, said that, oh, the Intel people just gave them the TLA plus specifications, and that's what they worked from. They said, oh, this stuff is neat. We'd like to do another level of refinement in TLA before we go to the RTL code. But I never heard how that went, whether they did it or, and even I've lost contact with Intel, so I know nothing about what goes on there now. Yeah. By the way, one problem is that industry does not talk about what they do. And that paper by the Amazon people was written because I urged them to do it. I had no input as to what they actually wrote, but I said it would be really neat if they could, write a paper about their experiences. And they somehow managed to get management at Amazon to agree to let them do that. But that's very rare.
Hi. So from a I guess very junior computer scientist, how do we I guess better train ourselves to model things mathematically rather than to think in programming languages and those data structures? Yeah.
Okay. Well, unfortunately, the only way I know to do it now is for you to get the TLA plus training materials. And the best way, I've produced a series of videos that I think is the best introduction. And I really think that this stuff is important enough that undergraduates should be taught how to think about their algorithms and about their programs this way. And I would like, unfortunately, I don't know how to get that to happen. I know one of the problems is that doing this requires learning to think mathematically and to think about mathematics and use mathematics. And mathematicians do not teach that. For example, as I said, you have to write things in a formal mathematics, completely precisely. And you don't learn to do that in a math class because, mathematicians don't understand how to do it. So, one thing you could do is to tell your math professor, I don't want to do math with all these words. Show me how to do math in real mathematics with formulas. Because, well, let me tell you something that happened. There's a thing called, well, I gave a lecture once at an audience that was half mathematicians and half computer scientists. And these were all, graduate students or above. And there was, as a selected audience, they had to apply to go to this summer school, to this little course. And I wrote a simple formula, a little bit more math than the ones I've showed you, but not much. And then I said, who could understand this formula in real time? And about half the members of the audience raised their hands. And then I said, okay, all the mathematicians, drop your hands. Almost no hands were left. So we had, and this was, the stuff that they learned in their freshman math class. And these were graduate students, postdocs. And the computer scientists just did not, were not that, just familiar enough with simple math to be able to read a simple formula in real time. And that, I find that scandalous. And you should, and mathematicians just don't understand this. You've taken most of you have probably taken calculus, and you've learned the Riemann integral. Well, you may not call it the Riemann integral. It's the definite integral that you use, that you learn how to compute in freshman calculus. And question I've asked mathematicians is to say, how long would a completely formal definition of the Riemann integral be? Just assuming the addition, multiplication, and stuff of real numbers, and then just ordinary, simple, usual math like sets and stuff like that. How long would it take to write that definition? And the answers I've gotten have ranged literally from 50 lines to 100 pages. The 50 lines was something of an outlier. Most of them were in the well, 50 lines is a page, I guess, but most of them are, the lower lines, so several pages. The definition of the Riemann integral in TLA plus takes about a dozen lines. But mathematicians do not understand, that it is really easy to do the mathematics that they teach to undergraduates completely formally. And there are real reasons. Let me try to say this. Suppose I give you this sentence. For all fruit there exists there is a worm that eats it. And then I say, well, what's the negation of that statement? Is it for all For all fruit, no, there's no worm that eats it. For some fruits, there's some worm that doesn't eat it. Most people, I mean, you'll be able to figure, I presume most of you will be able to write that negation. Most people, you know, can't. But then if I gave you something like, that was something like, if you've seen the delta epsilon definition of limit in calculus, if I gave you that, you wrote it, and, you know, in words, you know, for every blah, blah, you'd have to think a while to figure out what the negation is, and then most students couldn't do it. Well, if you wrote instead of writing in words, for all, you wrote that for all symbol, you know, upside down A, and you used upside down E for the exists. And then there's this simple rule that not for all equals exist not, and not exist equals for all not. You would just sit down and write the negation and turn it into English in no time. But because you didn't learn, people don't learn that when they learn quantifiers. You know, they may learn about them in school, but they don't learn how to use them in practice. Using math becomes difficult for them. So get your math teachers to really teach you math and to stop writing things in words. And as a footnote, if they have you writing proofs, tell them to read my paper, How to Write a 21st Century Proof. Because you think that it's bad the way they write, you know, formulas. At least they'll write, you know, 2 + 2 equals 4 in a formula. They don't even do things that simple in writing proofs. They're really stuck in the 16th century, the 17th century, in the style, in the way they write proofs.
Okay, any more questions? Okay, if not, let's join me in thanking Leslie for the wonderful talk. We have refreshment out there, so if you want to mingle and hang around and hang around.